All right, so topic 8.2 is on connecting the position, velocity, and acceleration with integrals. So over on the side, the position function can be written three ways. One way is using S of t. However, if the particle, like a lot of times there's a particle moving on the x-axis, and they'll call it x of t. Particle moving on the y-axis, they'll call it y of t. You probably remember that from before. So what is the derivative of the position? Velocity, good. All right, so the second derivative of the position is the derivative of the velocity, which is also acceleration, good. Okay, so we practice a lot going that way. Okay, so now we are going to go the other direction. So if you, if you have the acceleration and you want to find the velocity, you can find the integral. So you can use integration to go the other way. Now you will need to know like one value. Like if you have acceleration function and you want to find velocity, you'll need to know like the velocity at least one time, and then you can find it. Or if you want to go from velocity to position, you'll need to know the position at one time, and then you can find it. So let me show you what I'm talking about. So on number one, we have the acceleration function of a particle moving on the x-axis. We know that the particle's velocity at 18 centimeters per second at t equals 2. And we know that the initial position, so when time is 0, where the particle is at 8 centimeters. And so the question is, what is a function, x of t, that represents the position of the particle? So we have to take a couple of steps to get there. So we can go from acceleration to velocity by finding the integral. So we'll start with that. So v of t is going to be the antiderivative, or the integral, of a of t dt. Now, which is nice, a lot of these are polynomial functions, and so finding their integral isn't super challenging. And the ones that aren't, we're probably going to use the calculator to find it. So the actual calculus stuff we're doing today, I don't think is going to be crazy difficult. Okay, so we are going to find the integral of this by adding 1 to the power and dividing by the new power. Okay, and so now I'm going to go back up and use what I highlighted in yellow to figure out what t is. Bless you. And so I know, I wrote my t sideways. I know that at time t equals 2, that the velocity is 18 centimeters per second. So I'm just going to go ahead and put 18 in for the velocity and 2 in for t. Right, and then this shouldn't give us anything too crazy to do without a calculator, because a lot of these problems are written nicely where you don't end up with a bunch of weird fractions. And so that would be 6 times 4, 4 times 2. And then when I get everything on one side, it looks like we're going to get that c is 2. So now I can write the velocity function. Now sometimes that is what the directions are. It is to write the function for the velocity. And that's what that would be, but we need to go one step farther and find the position. And this is a particle moving on the x-axis, so we are going to call the function, the position function, x of t. And it's going to be the integral of v of t dt. All right, so you guys try to find that integral or antiderivative on your own, please. Right, and then I'm going to use what I highlighted in pink to find what C is. Now, when it's initial position, that makes it a little bit easier to find C because all of these things are going to be zeros. I'm actually going to write them in as zeros, but just for your notes, but you probably can just already tell that C is going to be 8 here. All right, and then I'm kind of running out of room, but I can write my position function by taking that 8 and putting into this light blue function for C. All right, any questions on that? Okay, so that's the main new thing we're going to do today. We are also going to talk about total distance and displacement in a second. So that's also going to be new. And then we're going to use an old formula that we've done before to use an initial position and add an integral to it to find another value of the function. Okay, so on example 2, Mr. Brust is driving across town to Mr. Sullivan's house to play with a new set of Star Wars figures. Mr. Brust's speed would obviously vary throughout the drive, but because he is so cool, he came up with a function that represents his velocity in miles per minute at any time t minutes since he left his house during the 30-minute drive. So this is 5, 10, 15, 20, 25, 30. All right, and then this is the graph of the velocity. So he starts off with a negative velocity. What do you guys think that means? Say it again.
Put it in reverse?
No. So he would be slowing down if his velocity and acceleration were working against each other. So if there was a positive velocity and a negative acceleration, he would be slowing down. What does a negative velocity mean? It doesn't mean slowing down. It's direction. So he starts off, I don't know this Mr. Brust, but he starts off driving in the wrong direction. I don't know. All right, and then he is driving in the right direction, and then he makes a wrong turn. I don't know. And then he eventually ends up where he's trying to go.
It's like me trying to get out of Murfreesboro.
Maybe that's what it is. He's avoiding traffic. Sometimes it's worth it to drive in the wrong direction to avoid traffic. Okay, so we're going to set up the expression for the following scenarios, and we'll just use our calculator because this is, I mean, we could definitely do this by hand, but it would be annoying, especially with a decimal there. So we want to know how far is Mr. Brust from his house after 10 minutes. All right, so this is kind of Like this is a rate, and if we want to find how many miles he traveled in a certain amount of time, we can just do the integral from 0 minutes to 10 minutes of his velocity function. And that will give you the total number of miles that he traveled in that 10-minute span. And we've definitely done that before. It's been a little while. I think we were talking about that when we were like, we knew the rate that the snow was falling and we could find how much snow had fallen during that time. All right, so let's go ahead and put that function into y1.
I forgot how to do natural log.
Okay, ln is right beside 4, or ish.
Oh, I see.
And then we'll just go to alpha window, choose number 4. And since we saved that function as y1, we can just pull it up. And that will give us how far away he is from his house. All right, and then 15 minutes, same exact thing. Except, obviously, not exact. We're going to change the 10 to a 15. And then the last one, if Mr. Brust arrives at Mr. Sullivan's house after 30 minutes, how far away does he live? What do you guys think? 0 to 30, good. Wait, is that what you guys? Oh, yeah, that is what I got. Sorry. Okay, is that the same question that he's asking on part D?
No.
It isn't, because remember, he starts off driving the wrong way. So what we found is the net change. So at this point, this wasn't the distance, like how far he had driven the whole time until we got to 15 minutes. It was how far it was from his house to where he currently was. That is called displacement. So let's fill in this box for a second. The antiderivative of the velocity is displacement, which is also net change. Okay, now if I want to find the total number of miles that he has driven, that's going to be the integral of the absolute value of the velocity. And so this, these areas down here that we would subtract, they actually get bumped up to become positive areas. And like same thing right here, where I would subtract that, is going to get bumped up to be of a little positive area. But when you're using a calculator, it's super easy. We're just going to put that y1 in absolute value bars. And absolute value is found the same place. Oh, I don't know. Sorry. Is found the same place we go whenever we find the integral and the derivative stuff. It's this number 1, this absolute value. So I can see if I can just be lazy. Not super lazy. All right, so once I get in these parentheses, we're going to do the absolute value of y1. Keep hitting the wrong button.
I got the same thing, right? No, I did not.
Okay.
I thought I did not.
That's okay. So he definitely drove more miles than the distance it was between them.
My calculator is having an error.
It does take a long time for your calculator to calculate that. It must be really confusing for it.
I think it is because it's just.
Eventually, it should get there.
Yep.
Okay, so we also had the absolute value of the velocity another time. Do you remember what it is when you're not doing the integral of it? It's going to be a rate of change that doesn't have direction. Just speed, yeah. It's okay. Okay, so let's get through a few more examples. All right, so a particle's velocity is given by this function. It's another nice, pretty polynomial. The function x of t represents the position of the particle along the x-axis. So we're going to find the position of the particle after 3 seconds if x of 0 is 5. Now, we could just find the position function like we did from basically from here to here, and then plug in 3. But there's another way I want you to remind you that you can do it if you want to do it that way. I personally prefer this way that I'm going to show you, but you can do it either way. So we did this before when we were wanting to find something like x of 3, and we had an initial condition where we had some information about the problem, like this one. We know that x of 0, we know what that is, and to it we add a rate that is going to accumulate, in this case it doesn't say what it is, but accumulate units on the x-axis.
So 0 to 3?
Yes, and so whatever was here goes there, and whatever is here goes there of the velocity function. Now, for this to work, this does have to be a rate of change function, which it is. All right, and then we can just figure all this out. So we know x of 0 is 5. All right, and then we can find the antiderivative of v of t by using the power rule. All right, and then on this one, I am going to need to go back and plug in 0 and 3. All right, so I'm going to plug in 3 and raise it to the 4th, cube it, and multiply by 2. And then it's just a regular 3. What happens when I put in 0? It's just all zeros. Good. All right. So then I know if I add these two, I get 84, subtract 54, and so that's going to be 30. And then in the end, the position at t, whatever, 3 seconds, is going to be 35 units, I guess, on the x-axis. All right, any questions on that? All right, and then B is the same thing, just a different, well, I guess maybe it's a little more challenging. No, it's basically the same, sorry. So this time we want to know x of 2, and we know x of 1. Right, and then I'm just going to make this a -2. And I already found that integral, so I don't need to find it again. I am going to jot it down, but don't have to actually do it. All right, and then we'll just plug in, we'll just plug in our 1 and our 2.
Why is it 1 and not 0?
Okay, because this time we know x of 1.
Okay.
Yeah, it's a whole new problem. Same particle, just a different information that you're given. I wrote a 3 where I was supposed to write a 2. So it looks like at that time, at 2 seconds, the particle is at the origin. Oh, not necessarily at the origin, but yeah, at the origin if it's on the x-axis. All right, y'all good? It's taking longer than I thought it was going to. All right, so on number 4, we want to know the total distance traveled by a particle during the first 4 seconds if the particle's velocity function is given by b of t equals -1.5 t plus 3. And so this graph is that function. Let me do a different color. Okay, sorry, I'm gonna write it one more place. All right, so if I wanted to just find the displacement, I would just use this function. But I want to find the total distance, so I need the absolute value of this function. And so if it is above the x-axis, then we're fine. But when it's below, we actually kind of like flip it up. This one is y equals, and so that ends up becoming positive 1.5 t. And then what do you guys think about the 3? It's -3, yeah. All right, and so what I'm looking for here is this area. Oops, I didn't mean to do that. We're doing 4 seconds? Yeah. In this area. which we can definitely find, but it does tell us to set up an integral and show our work. So I'm going to set up the integral. I'm just trying to think of, if you have a graph of it, showing your work could be just finding the area. I think that's fine. Okay, and so this point right here looks like it's 2. That would be the point 2, 0. If I plug 2 in for this t, do I get 0? Yes, so that is that point. So one of your integrals is going to be from 0 to 2. All right, and then what function would I use for that one? Would I use the original v of t, or would I use the opposite one? Original. All right, you guys set up the second integral that would give us this purple shaded area. Don't forget your dt. I forgot mine. Sorry. Okay, and so to show my work, I'm going to do 1/2 base times height. Oh, wait, hold on. All right, so it's going to be 6. All right, any questions? Okay, one more to go. All right, so the graph to the right shows the velocity of an object moving along the x-axis for a 5-second period. A wants us to find the total distance traveled by the object over the 5-second period. Okay, and so what I'm going to do, if I do total distance, I am going to find these areas, but am I going to use the negative or the positive for those ones under the x? If I want total distance traveled, we want positive. Good. All right, so all I really need to do on this is figure out these areas.
Would it be a stretch to do like the rectangle and then a tiny little baby triangle?
Yes, that's what I'm doing. I'm doing a tiny baby triangle. What do you guys think the area is? Tiny baby triangle?
That's like 1/2 times 1/2 times
1.
So 1/4?
Yes. Okay. Oh, I keep writing 1/2 instead of 1/4. I'm sorry.
Do you want us to put our answer in fraction or
I don't
decimal?
care. You can do 7.5 or you can do 7.5. It doesn't matter. Okay, and are y'all good? Okay, and then part B tells us that at time t equals 2, the particle is at a point where x is 10. Where is the particle at time t equals 0? Okay, so we are doing the same thing like we did up here, but we're going to do our integrals with areas. So we want x of 0. What do we know? What position do we know? 2. All right, you guys set up your integral, please. Don't forget, this is the graph. This is the graph of the velocity.
Can you move backwards, like go from like a higher one on the bottom to a lower?
You can. You can move backwards. It was a property we learned a while ago when we first started talking about integrals. So if the lower limit is bigger than the upper limit, we can fix it to be the right way. But what do we have to do? Change the sign. So then now it's going to be minus the integral from 0 to 2 of v of t dt. Okay, so this time I'm gonna erase this. I am just looking at this guy. So that area, wait, what? Oh, just kidding. This guy too. All right, so that's a 2. This is also now a 2.
So 10 minus 4.
Close. Because it is minus.
Minus negative 4?
Yes. So we're not doing an absolute value here. We're doing the actual stuff. And it's under the graph. Good. So that's a minus a negative 4, which is going to be 14. All right. What questions do you guys have?
Can I use the restroom?
That's not what I meant by questions, but okay.